So we have seen how to use lists, use for each to iterate through a list. We saw a simple example where we looked at the toppers across all the subjects. And then we also saw how to implement insertion sort, which is a way of arranging the elements in a list either in ascending or in descending order. So now let's put all these together into a somewhat substantial example, which is to correlate the performance of students. So we are interested in this hypothesis that students who do well in mathematics do at least as well in physics. So we need a way, of course, of objectively stating this English sentence. So one way is to say that students get, if they get a certain mark in mathematics, they get a higher mark in physics. But we felt that marks are too fine grained. Somebody who gets 87 in maths and 86 in physics need not be considered to be worse in physics than in maths. So what we said was, instead, supposing we assign grades. So we assign grades A, B, C, D in both the subjects. Then what we would like is that those who perform well in mathematics, so say they get the top 2 grades, A or B, then they must get at least the same grade, so the same grade or higher in physics. So if they get an A in maths, they must get an A in physics because there is no higher grade. But if they get a B in maths, then they must get a B or an A in physics. They can do as well, which is to get a B, or better, which is to get an A. Right? So this is our question. We want to ask whether this is true or not. Is it true that students who do well in maths do at least as well in physics in terms of this quantification over grades? So this is the algorithm that we proposed. First, we have to, of course, assign grades because we have only marks. So our grade data, the score data for the students has only marks. So how do we assign grades? Having assigned the grades, then we need to come up with students who have A's and B's, right? So in particular, we need all those students who got an A in maths, those who got a B in maths, those who got an A in physics, those who got a B in physics. So there are 4 lists of students that we have to construct once we decide how to award grades. Now we have to do this hypothesis validation. We have to check whether this hypothesis is true or not. So the first step is to check all those students who have got an A in maths. In order for the hypothesis to be true, those who have got an A in maths should also have got an A in physics. So you want to count how many students who have an A in maths also have an A in physics. So this gives you a number of students from that category who support the hypothesis. Secondly, you go to the list of B grades in maths, and now you check how many of these students have got either a B or an A in physics. So these 2 counts will give us a list of how many students confirm the hypothesis. Those who are not in this list but who have got an A or a B in maths will be those who do not confirm the hypothesis, and therefore by counting how many of them confirm versus how many of them do not confirm, we can come up with some measure of how valid the hypothesis is. If an overwhelming number of them confirm, then we can say the hypothesis is true. Such a hypothesis is never going to be 100% true, right? Because this is based on human beings, and human beings have different kinds of things which drive them. So we can't expect that such a hypothesis will have 100% confirmation. But say, for example, 80% of the students follow this, then you can say that it is reasonable. If only 50% do it, then it's like a random chance, right? Only half of them get better, and so the other half get worse. So there's really no correlation between maths and physics. So that's what, so we are not presupposing, we want to find out from the data whether this hypothesis is valid or not, for which we need to execute this computation. So the first step in this computation, as we said, is to convert marks into grades. So we are going to take a simple-minded approach, which is we are just going to give equal numbers roughly of A's, B's, C's and D's. So we are not going to look at the relative performance in terms of how well they have done compared to each other, but we are just going to ruthlessly cut them off at 1/4. So in our grades data set, we actually have 30 students. So roughly this means every group will have 7 or 8 students, because you cannot divide 30. If there were 32, then there would be 8 in each category. Since there are 30, some will have 7, some will have 8. So we first need to get this quartile things. So to calculate these quartiles, we need to find out who are the top 1/4, then the next 1/4 and so on, right? So the easiest way to do this, as we said when we discussed sorting, is to actually arrange these marks in ascending order or in descending order. Once they are arranged in ascending order, we can take the first group, the first 1/4 in this list, and call that the highest or the lowest depending on whether it's ascending or not, and the next highest and the next quarter and so on. So we can break up this sorted list into 4 equal segments, and each segment will correspond to 1 grade. So one of the things that we will need is not just the list of marks, because we need to check the marks in physics against the marks in mathematics. So we need to know a student who has got an A in physics, an A in mathematics, whether he has got an A in physics, he or she has got a B in mathematics, whether she has got a B in physics or an A in physics. So we need to associate with each mark also the identity of the student, right? So we have in the data set, we have the sequence number of the card, the 0 to 29. So we can use that to identify the student. So if, say, student number 7 has got an A in mathematics, we want to check if the same student number 7 has also got an A in physics. So that means that this list that we construct of marks, which we are going to sort, right, doesn't have just marks as its entries. It has these pairs, right, these pairs which we will write as a 2-element list. It has the first element of the list is the student ID, the sequence number, and the second is the marks. So now when we are comparing for getting the sorted marks, we don't really care. The student ID is used only when we confirm the hypothesis, when we check every student who has an A whether they have got an A there or not. But to actually award the A, we are not looking at the student ID, right? So we will come back to this later on, but let's first look at how to get these marks lists for a given subject, right? So it's easy enough. We just do our usual thing. We start with an empty list, right? And then we process the table. And for every row in the table, we just pull out 2 fields, the sequence number, and we are now using this across subjects. So we will use it for mathematics, for physics, and for chemistry separately. So depending on which subject we provide, we can even do it for total marks if we want, but we are not using it in this example. We are only using mathematics and physics. But any field which is there on that card, we can extract a list of the sequence number and that field value, right? So this builds the marks list. So what we want to do is initially build the marks list for maths and the marks list for physics, right? So when we build the marks list for maths, we will get sequence of pairs of this form. So we will have S1, the sequence number of the first student and the marks of the first student, then S2, M2, and so on, right? So this is what this list will look like. So this is in no particular order. This is just in the order in which we process the table. Now we need to sort it, right? So we could use insertion sort. But as we said before, the problem with insertion sort as we have defined it is that it doesn't have a natural way of comparing the entries in our lists, because now we don't just have marks, we have this, each entry is a pair ID comma marks. So we want to look at I1 M1 one pair, I2 M2 another pair, and compare it. But what we are really interested in is whether M1 is smaller than M2 or not. We are not really interested in I1 and I2. So we need to be able to take this list and extract out only the M1, M2 part. So for this, it's useful to just add a new function or an operation which allows us to do this, right? So in general, we might want to extract things at various parts of the list, but I think it is reasonable to assume that we can look at the first element and the last element of the list quite easily. So let's call these first and last. So first of L will give us the first element in the list, as you would expect. And last of L will give us the last element in the list. So if I have a list 1, 2, 3, 4, then first of L will be 1, last of L will be 4, right? So first gives us the first item, last gives us the last item. So if I take, for example, this kind of a thing, right, and I apply first to it, I will get the ID, and if I apply last to it, I will get the marks. Now, it will be useful to also look at what happens to the rest, right? So if I do first and last, then I have the remaining part, right? So I take out the first, and then I have the second onwards. So I will call that the rest. So the rest is a list. First is an item, rest is a list, right? So if I take rest of 1, 2, 3, 4, it is the list 2, 3, 4. First of 1, 2, 3, 4 is the item 1, okay? It's not the list 1, it is the item 1, but the rest is a list. Similarly, if I take last of 1, 2, 3, 4, I get 4. So I can take the initial part, which I will call init. So init of the list will be the list 1, 2, 3, everything except the last one, right? So now that we have this in place, let's do this minor modification of our insert procedure, which takes into account the special nature of our information. So we don't just have simple numbers to compare, but we have these pairs of numbers. So what we do is we have to change only one thing, which is when we decide on whether to shift or not, whether we decide to insert x into the new list or to bypass it and go to the next z, instead of comparing x to z directly, so remember now x will be of the form ixmx, right? It will be some pair, and this will be of the form izmz. So what we want to do is compare mx and mz, right? So this is why we use last. So we say, is last of x smaller than last of z? This is the only change we have to make. So in general, if I apply sorting across different types of values, the main thing I need to change is the comparison. How do I compare these values? So depending on how I compare them, that if condition alone changes, everything else is the same. Once I have compared them, everything else is the same. I shift them to the new list, I insertion sort, everything is the same, right? So this is the only change we need to make to our original insertion sort in order to accommodate this special data that we have. So once we have done this, right, now we have built this maths marks and the physics marks by calling that build marks list procedure. So then we can use this insertion sort, the usual insertion sort, but with the new insert function. That insert operation is updated to use last instead of just x, right? So insertion sort using this updated sorted list insert will give us a sorted maths list and a sorted physics list. So once we have a sorted maths list and a sorted physics list, we can get down to this business that we are really interested in, which is to assign grades, right? So we are trying to assign grades. So the reason we are sorting all this is because we want to take the sorted list, right, and we want to divide it into 4 groups and say that this is A, because it's an ascending order. So the leftmost will be a D and the rightmost, the highest marks will be an A, and we want these to roughly be 1/4, okay? So this is our strategy for awarding grades. So we are going to create this simple grade assignment. So I'll tell you why it's a simple grade assignment in a minute, but we are going to assign grades to a sorted list by this quartile, right? So first we have to, so quartile is just a position, now that it's sorted, right? So quartile is just defined by the position. The first 1/4 of the list is the bottommost quartile, the next 1/4 is the third quartile, next 1/4 is the second quartile, and so on, right? So the first thing to do is identify these quartile boundaries, right? So there is a function here which we have not seen before, but which is obvious, right? So we will assume that with lists we have this length function. So the length function just tells us the number of elements in the list. So that means we don't need to know in advance how many elements are there. Of course we can compute length by saying for each x in L, and we can take a counter and say count equal to count plus 1, and we can find out the length. So it's not that we don't know how to find the length just using what we already know, but it's convenient to assume that we have this length function given to us, right? So the class size is given by this length of this marks list. So everybody has been accounted for. So this L could be either the maths list or the physics list. All we assume is that it's a sorted list, right? So we assume that it's sorted and in ascending order. So since it is sorted and it's in ascending order, the first quarter is the 4th quarter. So the boundary of the first quarter, Q4, is the class size divided by 4. So supposing there are 30, then this divided by 4, this will give you 7.5, which is not an issue because we will see as we go along. Then the boundary of the 3rd quarter, where the 3rd quarter ends, the 2nd quarter begins, is going to be 15. And the 2nd and 1st quarter are going to be at 3/4 of this, so it's going to be at 22.5, right? So this is going to be Q4. This is going to be Q3 and this is going to be Q2. So these give me positions with respect to the overall list where these grade boundaries come. So that's the first thing I compute before I start assigning grades. Okay. So let's assume we have done that. Now the next thing is I have to construct these 4 lists, right? Who all have got an A, who all have got a B, who all have got a C, who all have got a D. So I will have 4 lists, grade A, grade B, grade C, grade D, and I will assign them all to be empty. Now I will go through the list and I will keep track of the position, right? So I start with the 0th position. So it's conventional in computing to start with the 0th position. So I'll start with the 0th position, right? And I will check whether that current position that I'm looking at, whether it is in the first quartile, that is bigger than Q2. It's in the second quartile, means it is less than or equal to Q2 and bigger than Q3. Third quartile is less than or equal to Q3, bigger than Q4, or it's in the fourth quartile is less than or equal to Q4, right? So this is very similar to what we did when we did this third max. When we did this third max, right, we tried to find out which zone the new value came in. So here we are not going to update anything, we are going to insert it into the correct list. So if it is in the first quartile, then we put it into the grade A list. If it is in the second quartile, we put in the grade B list. So all these things are identical except which list we are updating. So the new X that we are processing, right, does it go into grade A, grade B, grade C or grade D, depends on whether its position is above Q2, between Q2 and Q3, between Q3 and Q4 or below Q4, right. So in this way, for each position I will do this and I will keep incrementing the position. So I will walk through this list from beginning to the end. So this is an important fact about lists that we have to keep in mind, that when we do a for each, basically it walks from beginning to end, right. There is no way to directly go to the 17th position. You have to walk through 16 positions to get to the 17th position. That's an unfortunate fact about lists, right. So lists are a sequence which are built up in this sequence and you have to read them in that sequence. So for each will only allow you to go from beginning to end. There is no way to directly jump in. That will be a different data structure which we will see later on. So at the end of this, I have got these four grades, right, grade A, grade B, grade C, grade D. They are roughly equal. Now I have to give them back. I have to tell you what the grades are. So the way I will do it is just to create a new list which consists of all these four lists together, right. So the simple grade assignment will return four lists, the A list, the B list, the C list and the D list. So I will get back not one list but four lists packed together in a single list, a list of lists, right. So a list can contain anything, in particular it can contain lists, right. So that's what this gets. Now why is this a simple grade assignment? Well, we already saw when we actually did it with our data set, when we did this by hand, that this is not a very nice way to give grades, because there could be marks at the boundary which are duplicate, right. So the person who the highest C grade and the lowest B grade may have the same marks, right, because we are not saying that all marks, if all marks are distinct, everybody gets a different mark, then at least you will have some consistency that two students with the same mark will get the same grade, because there are no two students with the same. But if I have two 62s and one 62 happens to be at the top of the Q3 boundary and the other one is the bottom of the Q2 boundary, one will get a B and one will get a C, and that's very unfair. So what we did when we did it by hand was we adjusted these boundaries by hand to go to a nearest reasonable point where everybody so either we moved it to one side so that the D grades became low, or we moved it to the other side so the C grades became high. So depending on which way it looked more reasonable, we did some hand adjustment, right. So coding that hand adjustment is not very easy, as you can imagine. That's why we have assumed this very simplistic thing, but this is not really how you would assign grades even if you are going by quartile, because you have to pay attention to this fact that students at the boundary of a quartile could have identical marks on either side. But anyway, leaving that aside, let's assume that this works. So we have now taken the sorted list of maths marks, right, and created four lists of maths marks with A grade, B grade, C grade, D grade. Similarly, we have taken the physics marks, right. So we can take the maths grades, we can take the simple grade assignment, pass it the sorted maths list, and it comes back with these four things. Similarly, we take the sorted physics list, comes back with these four things. Now we have to unpack these four things, because we don't want four lists. We want the A list, the B list, the C list and the D list separately, because we need to iterate over them separately, right. So how do we unpack? So this is where we use all those fancy things that we did, right. So we talked about first and last, and we also talked about init and rest, right. So supposing I take a list, right. So supposing it has x1, x2, x3, x4, it has four elements, right. So if I take first, then I get x1, right, and then we said that this is the rest, but the rest is also a list. So if I take the first of the rest, then I get x2, right. So the first of the rest of L is the second element in L. So what we are saying is that the maths A grade, so remember the grades were given as A grades, B grades, C grades, D grades, a list of four values. So the first value in that list is the A grade. So I take the first of the maths grades so this has got A, B, C, D. It's got four lists coming back. So the first of those is the A list. Now if I take the rest, okay, that is everything except the first, and I take the first of that, then like we saw here, that gives you the second value. So that is the B grades. Right. So by using the first and first of rest, I get the first value and the second value. Similarly, from the other side, if I take the last value, I get the D grades, and if I take the init of that, then I get up to the third position, and then the last of the init is the third position, right. So the init will give me 1, 2, 3, and last of that will give me 3. So that will give me the C grades, right. So by this clever use of first and rest and last and init, we can extract these four quantities. Right. Of course, if you want the third grade, you can get from the front also by taking rest and then taking rest of that. So you take rest twice, that knocks off 2 elements, and then you take the first, right? So by doing this combination of first and rest, you can actually get to whichever position you want. But in particular, if you just want the first and last, it's very easy. If you want the second last and the second also, it's quite easy, as you can see, right? So we do this for maths, we do this for physics also. So again, the A grades in physics are the first, the D grades are the last, the B grades are the first of the rest, and the C grades are the last of the unit. Right? So now we are where we want to be. This is what our goal was. We wanted to separate out the students into those who have got A in maths, B in maths, C in maths, D in maths, and those who have got A in physics, B in physics, C in physics, and D in physics, right? So after all this hard work, by first extracting the marks from the data set into lists, then sorting the lists, and then after sorting the lists, partitioning them into these quartiles and assigning grades, and then unpacking these grades back into 4 lists, we have finally got the list that we want. Now in this, of course, we are not interested at all in the C and D grades, because we are only looking at the well performing students. So students have got at least A or B, but in the process of doing those 4 lists, we have got 4 more lists, so it's no harm. Anyway, we will continue, right? So now we have got these 4 things. So the first thing we have to check is how many students who have got A in maths have also got A in physics. This is just our familiar for each, right? We have to do a for each x in maths, for each y in physics, check if x is equal to y. Only thing is we have to keep track of whether we found the x or not, right? Earlier we were only keeping track one way. We were only keeping track of those things that we found. For instance, when we are looking for students who are born in May and live in Chennai, only if they satisfied both, we added them to the list. If they did not satisfy, we just threw it away without remembering. Similarly, when we were looking at students who are toppers in all the subjects, if somebody was not a topper in all the subjects, we didn't care. But here we want to know how many confirm and how many do not confirm, right? So for that reason, we will actually keep track of whether we found it or not. So we have a variable called found, right? So if x is found in, if x from maths, an A grade student in maths is found in physics, then we set found equal to true. And for this same x, if we exit this loop, we go through all the physics students and we have not found it. If it is not found, then we put it in a different list, right? So we have a confirm list. Confirm list are those students who have confirmed our hypothesis. Reject list is those students who have rejected our hypothesis, right? So in this way, we are using this variable found. We can keep track of whether they go in the confirm list, which is easy, or whether we have not confirmed them, which is what this found is telling us, in which case we put them explicitly in the reject list. Now one other advantage of doing this is that when we have found it, right, we can actually also stop looking at the rest, right? We are not going to find the student again. If we have not found it, we have to continue. But if we have found the student in the physics list, obviously the student is not going to appear again, so we can leave the loop. So it's convenient to actually add a way to get out of this iteration, right? So we will just assume that we have this extra command called exit loop, which kind of aborts this for each loop at this point and comes out. So what does it do? It goes to this for each where you found it, and it comes out to the end of that for each, right? So that's what it does. So there is also an outer for each, right? So that for each continues. The exit loop is inside a for each, so you go to the nearest the for each inside which the exit loop is, and that for each, it's as though that for each is abruptly terminated without processing the remaining elements. So whatever you have seen so far is done, but it's like you skip ahead to the end and proceed as though you have finished, even though you didn't see the remaining elements. So this is what happens for the A grades. So for the A grades, you check if they are in the A grades of physics. We have to do the same thing for the B grades, right? Except that we have to check for the B grades in maths whether they are in A in physics or in B in physics. So the first part is the same, right? So you will check. So we have every x who has got every student who's got a B in maths. So the maths B grades. We first check for every y in the physics A grades. So has the student got as much as an A in physics? If so, you're fine. Again, you set a variable found. Now if you have not found it in the A grades, then you check in the physics B grades. Again the same loop, only you do it only if you have not already found it, because it's wasteful to do this otherwise. In both cases, if you find it, you exit, right? So you exit the physics A loop, you exit the physics B loop, and finally if you have gone through both these loops and not found it in either of those things, your variable found is still false. In that case, you put it into the reject set, right? So it's just two nested iterations, one after the other. First check B with A and then check B with B. And if it's not in A and it's not in B, then you put it into reject. If you found it in A or in B, then you put it into confirm, right? So at the end of this two loops. So you have two loops which I kind of overrode. So the first loop said all the students who got A in maths, whether they confirmed or rejected. Then all the students who got B in maths, whether they confirmed or rejected. Right? And after these two things, now we have these two lists: confirm all those students who confirmed the hypothesis, all those students who rejected the hypothesis. So what we want is the number. We don't need to know who the students are. So as we said before, we can take the length of that list. So the length of the list confirmed will tell us how many students actually had done at least as well in physics as they had done in maths, and the length of reject will tell us those who did not. So this is the total number of students, right? So if we check the length of the confirmed list versus the total number of students, we will get a fraction. So if the fraction is something like half, it means that this is a totally random occurrence. Students who do maths well in maths may or may not do well in physics. We have no correlation. But if it's a large number like 0.8 or 0.9, it means that there is a good correlation between maths and physics, right? So that's the purpose of this whole exercise. But along the way, we have seen a lot of interesting things with lists, right? So to summarize, we saw one concrete use of sorting here, which is to identify these quartiles for grade assignment, right? So if we did not do this, then it would be very hard to figure out who are the top 25%, who are the next 25%. Once we sort them, we can just chunk that list into equal size bytes of 1/4, and we get the 4 grades, right? But one thing we saw is that because we needed to keep the list in a more complicated format, the elements are not single numbers, not just the marks, but these pairs of ID and marks, right? We needed to change our insert function to compare the second element of that. And for this, we introduced this new notation of first and last and init and rest, so that we can extract out selectively the beginning and the end of the list and the rest of the list which is left after removing these extreme elements. And finally, we saw that there is this exit loop which we can use when we want to explicitly abort a for each loop, because we have found what we wanted to find and there is nothing useful to be done by processing the lesser loop, right? And one more thing which was not explicitly mentioned anywhere but which was used implicitly is this length function. So we have also used this length function which allows us to extract the length of a list without going through it. Now remember, this length function you can easily do, right? So you can say count equal to 0 and then say for each x in L, count equal to count plus 1. Right? So at the end of this, for every time you walk through the list, every element you saw, you incremented count. At the end of this, count is going to be the length. So it's not that length of L is anything very complicated to calculate, but it's a nuisance to have to write this loop every time you want the length of a list. So it's convenient to be able to call this function.